So here are the requested solutions for all of the practice problems we've had at the conclusion of Unit 1. All right, so for starters, the cars in the parking lot. What we know is there are gasoline and electric powered and then alternative fuels. In deciding between trees and Venn diagrams, I'm choosing Venn diagrams for this one because I'm really trying to sort people into groups instead of having one event following another. What I know is there are a total of 18 cars in the parking lot. So I've already got that recorded down below. 14 of them are gas powered. The problem is I don't know which part of the circles those belong in. So my gas powered is 14. And 5 of them are electric. Same issue, I don't really know where those go. 3 are powered by alternative fuels, so I can put that number on the outside. I know that doesn't belong in either one of the circles. Well, if there were 14 that were gas powered, that means not gas is got to be 4 of them. Well, I've already got 3 not gas, which means there's got to be 1 more into the electric. Well, that's 1 electric. There's a total of 5, so that means there must have been 4 here. And there are 14 gas, so that leaves 10 here. So what is the probability that an alternative car has a gas-electric hybrid engine? Well, gas-electric hybrid has got to be in both of them, so it is 4 out of the 18 that I have. What is the probability that a gas-powered car is hybrid? All right, that's a little bit tricky there. What's the probability of being hybrid given that you are gas-powered? All right, so that is restricting my sample space. This is a conditional probability. So the probability that I'm hybrid is 4 out of the 14 that were given there. Now, here's an alternative way of trying to approach this Venn diagram. You saw the first time I was able to just sort of backwards count. Here's the second approach on this one. What I know is if I were to add the gas and the electric together, I know I'm going to double count that overlap region. So what if I add the gas and the electric and the alternatives? The alternatives is everybody on the outside. I know that would add up everybody in the entire region with one exception. I would be double counting the overlap. So in that case, I've got 14 plus 5 plus the alternatives, which is 22 cars. Well, there's 18 overall, so that means the overlap must have been the difference between those or just 4 cars, and there's the 4 cars right in the center, and then you can build up the rest of the Venn diagram. All right, next. There are 2 identical bottles. One contains green and red balls, the other one contains just red. Select at random. All right, so in this case, I think the better way to try to design this, because I've got to pick a bottle and then pick the balls out of the bottle, I think a tree diagram is probably better. So I've got bottle 1 or bottle 2, and each one of those could be selected with probability 1/2. If I choose the first bottle, I could either get a green or a red ball out of that. If I pick the second bottle, there are only red balls in that. So there's a 100% chance of picking a red here. In the first bottle, there are 3 balls altogether. 2 of them are green, so 2/3 chance here and a 1/3 chance here. I want to know what is the probability that the ball is red. So I'm really only interested in those 2 outcomes. The probability of coming out the first branch is 1/2 for the first choice times 1/3 for the second. The probability of coming out the bottom branch is 1/2 times 1. Total of 1/6 plus 1/2, which is just 4/6. All right. The alternative way that you could try to handle this one is, what if I came out this branch? It's the only branch that I didn't want, so I could solve this by complements. How about 1 minus the probability that I ended up there, which again turns out to be 4/6. Both approaches are equally valid. All right, here's another fun kind of counterintuitive problem. 2 families have 2 children each, and the father of the first family has got 1 boy, and the oldest child of the mother is a boy? Which family is most likely to have 2 male children? Okay, so be warned with probability problems. They don't always work out the best as you think. And I think, again, we're talking having one child, having another child. So in my personal opinion, a tree diagram is maybe a little bit better at dealing with this. I will show 2 ways, one for the father, one for the mother. So your first child could either be a boy or a girl. Your second child, no matter who the first was, boy, girl, boy, girl. All right, so what do we know about the father? The father has at least one boy, which means the only event that we can't use is the 2 girls. So the father has one of those 3 families. And what is the probability? And see, that's the father. So what's the probability that we have 2 male children, which would be the top one? So that would be 1 out of the 3 possibilities. So there's the probability that the father has 2 boys. All right, what about the mother? Well, I'll look at it in a slightly different way. How about this is essentially the results of the tree, but I'm just going to write them out just with letters instead of with a tree. I could have a boy, then a boy, boy, then a girl, girl, then a boy, girl, then a girl. What I know is the oldest of the mother is a boy, which is only those 2. So, my apologies here. So what I know is the mother is one of those, and the 2 boys is just that one condition. So the mother's probability is 1/2. The father's probability is 1/3. Who is more likely? The mother is more likely. All right, next. I think this one is an ideal candidate for doing Venn diagrams. In fact, I wouldn't even attempt to do anything at all with the tree. All right, so what I know here is that there are a total of 175. 73 say they want milk. All right. Problem with that is there's 1, 2, 3, 4 different regions where that could happen. All right, so I can't use that information yet. 97 want juice. Same reason, 4 places I can't go anywhere with that. 60 want fruit, 4 places, 1, 2, 3, 4 that I could go with that. I don't know how to fill that in yet. 19 say they want milk and fruit. Well, that's nice. Fruit, milk, well, there's still 2 regions. I can't use that yet. Of these, 11 want juice as well. All right, now I finally have something I can start using. That means 11 of them wanted the milk and the fruit, and then also the juice, which means those are the 11 right here in the center. But 19 wanted milk and fruit, so that must mean there were 8 additional ones, so I've already used that data point. All right, 34 want only milk. That's awesome. I can just fill that number in, 34. Now I can finally start doing some things here. I know this is 4253, but there were 73 altogether in the milk circle, so that leaves me with 20 sitting in that intersection. That's good, so I figured something else out. And then next, 36 want only fruit. So there's 36 down here. Add those up, 4755. But there were 60 who wanted fruit altogether, so that leaves me with 5 more down here. And I also know that the juice number was 97. If I add these up, 31, 36, subtract from the 97, that leaves me with 61 to go over here. So now I finally got my complete Venn diagram. I actually need to do one more safety check. I knew there were 175. If you go through and add up all 7 numbers here, that gets to 175. So I now also know that there are none left over outside. So anybody who is choosing a snack chose, at least from milk, juice, fruit, nobody chose anything else. All right, so that now means my probability problems are actually pretty straightforward. Juice only, well, juice only, that's this guy. So there are 61 out of the 175 possibilities. None of those, well, we just reasoned a few moments ago that there were none left over, so the probability of that is just 0. 0 out of anything doesn't matter, it's just 0. At least 2 different snacks. Okay, that's going to be all of the people right here in this middle intersection. They can't be on the outsides, they got to be right there in the middle. 31, 39, 44 out of the 175 wanted more than one snack. Milk, given that she wants fruit. Okay, milk, given that you want fruit. So we're into a conditional probability this time. Given that she wants fruit means we are in that circle, and wants milk, so I'm dealing with a restricted sample space. That is 19 out of everybody who wanted fruit, 19 out of 60. All right, next one. Are milk and juice independent? Okay, this is actually a slightly trickier problem. In order to prove independence, all right, so there's a key word. That bell should have gone off in your head. If milk and juice are truly independent, then the probability of milk given juice should just be the probability of milk if independent. All right, so is that actually going to happen here? All right, so the probability of milk given juice, well, there's my juice circle, and the milks in those are 31 out of the total in the juice column, which is 97. What's the probability of milk all by itself? Well, that was 73 out of the entire total, 175. Those two fractions clearly are not equal, so the answer is no, they are not independent. Knowing that somebody wanted juice does change their likelihood of wanting milk. They are not independent. Okay, on to the other problems. Is this possible? All right, the quick piece, is it possible that college students, well, what would it mean if you were able to multiply those two numbers together? It would mean the likelihood of being a college student and the likelihood of being an adult age 55 and older are independent. Well, if you go to any kind of college campus, then the majority of the people you're going to see there at college are students who are 18 to, let's say, 25, just making a rough guess. They tend to be very young adults. So if I know that you are on a college campus as a student, automatically my age assumption drops pretty significantly. If I already know that you are age 55 and older, then the likelihood that you are a college student drops pretty radically. These two events are not independent. Therefore, it is inappropriate to multiply their two probabilities. That's appropriate only when the two events are independent. All right. World War II. This is actually something close to reality. That 0.05 maybe not exact. The assumption of independence maybe not exact. RAF bomber crews did have to complete 30 missions in order to retire. So if I know the probability of being lost to enemy action is 0.05, then the probability that I'm not lost has to be 0.95, and this is actually really important. I was given independent. Because they were independent, I could multiply. What's the probability that you retire? Well, that's the probability that you don't lose your plane 30 times, and because they are independent, I can just multiply all those together. And so I had to do that 30 times. So this is 0.95 raised to the 30th, which is about 0.2146. What that means is there was slightly more than a 21% chance that a bomber crew would retire, or roughly 1 in 5 retired, 4 out of 5 were shot down. World War II, pretty brutal place. All right, Hawkins Sr. is applying to both Princeton and Stanford, totally made up probabilities here. And I need to show you two different visualizations. I'm going to choose a Venn diagram and a table, which admittedly are something of the same, but that's okay. Probability gets into Princeton. Well, Princeton is in 2 different regions. I can't really do that yet. Probability into Stanford is 0.5. 2 different regions, can't do that. Gets into both is 0.2. Okay, now I can use that. And Princeton was a total of 0.4, so that leaves an additional 0.2. Stanford was a total of 0.5, leaves an additional 0.3. Altogether, that's 0.7, so there's 0.3 hanging out on the outside. The other way I could have handled that is to think of these as, instead of probabilities or percentages, I'm just going to think of them as being out of a total of 100 people. All right, so probability gets into Princeton is 40%, which meant 40 out of 100 would get in, which gives me a 60 for free. Probability gets into Stanford is 50% into Stanford, so that's 50 people, leaves me another 50. Still can't fill in this piece. The probability gets into both is 20%, which meant 20 people were here, and that allows me to fill in the rest of the table. 20 plus 30 is 50, 20 plus 20 is 40, 20 plus 30 is 50, and as a safety check, those two do add to 60. I've got a totally happy table. And just in case you haven't been convinced yet that this is really just a Venn diagram, this circle was a positive into Princeton, which is here, positive into Stanford, which is here, and if you look at this, there's 20 in the overlap, 30 into the just Stanford, 20 into the just Princeton, and 30% hanging outside of both circles. So this piece right here really is just a tabular version of a Venn diagram. All right, what is the probability that neither university admits a student? Well, there's my 0.3 that was just hanging out on the outside, or 30 out of 100 if I do it this way. And show 2 different ways of getting the probability that at least one grants admission. Well, probability of at least one. All right, there's a couple ways. There's actually 3 different ways you could do that. One is, why don't I just add up those numbers that were all showing admission? So 0.2 plus 0.2 plus 0.3. Alternatively, I could say this was all of the people who got into Princeton plus all of the people who got into Stanford, subtract that overlap region because I know I double counted the people who got into both. And finally, you could think of this as a complement. Well, there are multiple ways to get into at least one of them, but there's only one way not to, and that's to be rejected. So I could say 1 minus the 0.3 that was hanging on the outside. No matter how you solve this problem, there was a 70% chance in this made-up scenario. Next, studies showing University of Utah trying to detect hearing loss. All right, I'm going to go ahead and add in a total column. So there were 60 ways for that. There were 40 ways for that. So there were a total of 100 people, leaving 42 and 58. What's the probability that the subject actually does have hearing loss? Okay, well, how could that happen? Actually has hearing loss. There's the 58 out of the 100 that were there altogether. All right, 2, what's the probability that a subject with a positive test actually has hearing loss? What's the probability of hearing loss given a positive test? All right, so we're back into a conditional probability again. So I am looking only at restricting my sample space a positive test. So positive test for hearing loss. The probability of hearing loss within that group is 54 out of 60. Next problem. All right, 10,000 athletes at the Beijing Olympic Games. The International Olympic Committee gave tests to 5,000 of those athletes. And there was some question, and here I've got a test being positive or negative, and you either were a user or you were not. And I'm going to use that total column just to simplify things. There was some question about whether the grand total should be 10,000 or 5,000. Well, the 5,000 I know, or I'm assuming, were either users and I have test results. For the total 10,000, I don't have test results, so I can't actually complete the table on that. So I need to worry about the 5,000 for this case. All right, so what I know is 2% of all athletes actually took the banned drugs. So that should be 2% here, which gives me 100 users and 4,900 non-users. And the International Olympic Committee is feeling really good. They got a test that's 99% accurate for non-drug users, even more strict, catches 99.5% of drug users. And so what we want to do, we got those 100 people and we want to catch them. So how can this play out? All right, so it's 99% accurate for non-drug users. So if you are not a drug user and the test is accurate, that means this is 99%. And it's 99.5% accurate for drug users. So if you are a drug user, then you should get a positive test. That would be the accurate result, so 99.5%. And now I've got enough information to fill in the rest of the table. All right, so 99.5% of 100 is 99.5. That wasn't hard, which leaves 0.5 of a person. And again, I'm just worried about the mathematics and the numbers. Everything else will work itself out. All right, if there's 99% here, then this is 1%. 1% of 4,900 is 49 people. And that leaves 4851 for the rest. And adding up my totals, this is 4851.5, and this is 148.5. All right, and so there's only, all right, strange, but only half a person who uses drugs who gets away, and you're feeling really good about this. I'm catching everybody. I may or may not miss a person, depends on which way this one rounds. I feel a little bit bad about that, about those 49 people who did nothing wrong. They were not users, but I'm going to catch them. I'm going to catch almost everybody who was a drug user, and so maybe I'm feeling really good about that. Let's see how this works out. What's the probability that an Olympic athlete who tested positive for drugs actually took drugs? So conditional probability. What's the probability that I am a user given that I have a positive test? So restricted sample space. I've got a positive test. The probability of users, well, that's 99.5 of those out of the 148.5. And when I get a decimal approximation for that, that's a 0.67. That's a little disturbing. There's a 67% chance that you are a drug user if you get a positive test, which means there's a 33% chance that you're not. That's really bothersome to me, and a really good question for you to answer is, can you tell me why, given such highly accurate tests, why is it that there's a 33% chance that you're not a drug user if you end up with a positive test? What is it about this scenario that makes that really counterintuitive result show up? All right, weird dice. Non-standard dice produce some really interesting outcomes. All right, die A, and these are just two different things. I'm going to go with the table. Seems like a pretty easy way to describe my sample space. Visualization showing which die has the larger value. Well, the only way, if B shows a 1, A is higher always. The 2s and the 6s beat every single one. 5s are higher whenever A is showing a 2. So those are B's. But these are A's because the 6 trumps the 5. So what's interesting here is die A has only 2 high dice. B die faces. B has 3 high die faces, but the reality is B is higher only in that section of the table. What's the probability that die A shows the larger face? Well, if I were to add up all of that, then I get 24 faces out of the given 36. So even though A has a high face on only 1/3 of its faces, it's higher 2/3 of the time. Kind of interesting. All right, extreme sculpting. All right, so now I've got 8 teams trying to win a competition, and it's this really bizarre reality TV. You never know what'll show up on reality TV. I've got 8 teams, and I'm going to let those teams be 1, 2, 3, 4, 5, 6, 7, and 8. And what I need to do here at 5 points in the competition, a randomly selected sculpture is blown up, but then that team can't be selected again. So what I'm going to do is I'm going to select random integers from 1 to 8. And I know there's only 5 rounds in the competition, but since a team can't be selected more than once, I'm going to do that until I get 5 different numbers. So that's how I have to handle the possibility that, like, when I randomly select a number from 1 to 8, it's possible that I might repeat one of those numbers, and it's actually, pretty likely that I repeat it in a string of 5. But I'm going to just keep selecting until I get 5 different numbers. So then I just need to run this simulation. Now I'm going to do this on so I've already described this in a way that the AP, 5 different numbers, I'm going to run this using my Inspire. Even though I've already described it sort of in general for the AP, the command that I'm going to use is a randint from 1 to 8. Now normally I would like to run this like 5 times, or since it was 2 years in a row, total of 10 times. I'm going to run it for 20 choices just to make sure that I've got enough to make sure that, like, I don't have any repeats. And I'm going to assume I need to figure out, like, what's the probability that this one team can survive. All right, so I want to know, assume team number 1 won both years. So I want to know the chances that team number 1 can actually survive this contest. It didn't matter whether it was team 1, team 2, team 3, like which team number you had is utterly random. So I'm just going to say team 1 is the one who won, and let's see what percentage of the time team 1 can survive through 5 different numbers per year for 2 years. So, let's see what can happen. All right, so over here on my TI Inspire, I have got a randint command, 8 to 20, 1 through 8, 20 times, and so I run that. That's slightly off the screen. Okay, so when I ran that command, note in my very first pick, it was like blew up 2, and then, all right, well, I can't use that one again. So the first 5 unique numbers are 2, 8, 3, 4, 5. There's the first year, and 1 wasn't chosen, and then 7, 8, there's a repeat, 5, 4, 2. So the first team was not blown up in the very first year. It did not show up in the first 10 unique runs. All right, let's run it again. 5, so, all right, 1 blew up the first year, so that didn't happen. 1 got blown up one time there. All right, 1, 2, 1 got blown up. 1 was blown up. 1 was blown up. 6, 2, 8, 3, 4, 6. There's the first year. 4, 1. All right, 1 got blown up in the second round. There's 6. 7, 7, 5. That's a repeat. 4, repeat. 1 got blown up in the first round. And 8, 4, 1 got blown up. So if I were to look at this, then 1 got blown up in all of those, but not the first, and there were 1, 2, 3, 4, 5, 6, 7, 8 different rounds. There was, at least from this trial run, 1 time when they didn't get blown up, 8 times that they did get blown up. So, like, I'm going to call it roughly a 1 in 8 for this simulation, and you can do as many simulations as you need to. The tricky part about this one, remember, is that there are repeated it's possible that you can draw the same number more than once, and so you need to be able to build that into your model, that I know until I get 5 different numbers. You need to handle the possibility that a random number generator might call a team more than once, even though that's not going to be allowed. We're not going to blow up the same team more than once. All right, so next, it would actually be really interesting for you guys, if you could, to try to build a model of this. If you had, like, could you actually compute the physical probability, the theoretical probability of surviving? And the answer to that one, let me scroll back here. The answer to that is 9 out of 64, the probability that they could survive for 2 years in a row, which is about 0.1406. And one, can you come up with that theoretical probability ultimately? And that's also really, really close to that 1 in 8 that we got by doing the experiment. Can you come up with that number? And the big question for you, and this will become a big question in all statistics, is 14% too rare? There is a 14% chance that somebody could actually go 2 years in a row without being blown up. Is that so rare that you're concerned about it? Big question for stats to come. All right, and then the last one, I am going to throw darts at a target. I know the percentage of the total areas. You're given 4 darts. So what I'm going to do is I'm going to call this region A, region B, region C, region D, region E, because that's going to be a whole lot easier for me. And percentage of total area, so how about I pick random numbers from 1 to 100 and let A, since A was 4% of the area, if I pick a number 1 through 4, that'll be region A. If I pick a number 4 through add on 12, 16, that'll be region B. So starting with 17 and adding on its 20 more brings me up to 36. D, starting at 37, adding on another 28, so that's 64. And E will start at 65, add on 36, so that's 65 to 100. And then what I need to do is select, and this time because it's darts hitting a board, it's possible to have multiple darts hit into one region, so that's perfectly fine. So I can select 4 random integers from 1 to 100 with replacement. The last one was without replacement. This one I can do with replacement because it is possible for a dart to hit into the same region more than once. All right, and then what you're going to do is on my calculator, I would probably run this using a randint 1 to 100, and because I'm throwing 4 darts, I'll choose that 4 times. And the way you, I'm not writing it all down in the space that I have, but the way the simulation would work is I do this, and for the 4 numbers that I pull out of my random number simulation, out of my random integer draw, I figure out which region they are in, and if it was region A, then we got 16 points. If it was region B, you got 8, 4, 2, and 1 point, and you convert the 4 random integers that were chosen into the points that were chosen, and then see if you get 20 or more. So entirely possible to do that simulation. Hope this helps.